Okay, and so tonight we're going to be going over chapters 12 and 13 as part of an exam review for Friday's exam on those two chapters. And so it's going to be covering rates and equilibrium. Okay, so before we actually jump into tonight's session, just to address Monday. So sorry, I was pretty sick Monday, so I didn't host SI. I will be posting kind of like a shorter video covering topics I wanted to cover on Monday. It might be posted tomorrow, but I'm also considering posting it on Friday. The reason why it's not really high priority is that video will cover chapter 14, which is not on the exam this week, and so it's kind of irrelevant in the context of this week and our priorities, but I do want you guys to have that information before next Monday's SI session. Okay, so it'll probably be posted either tomorrow or Friday morning. But again, if you're cramming for your exam on Friday, there's no rush to get to that video. No material in that will be pertinent to what your exam is on. Okay, so last Wednesday, our last session, I left you with some challenge problems. The first one, there was actually two little errors. The first one was probably the bigger error. Actually, they were both pretty big, but the pressure, I wrote P of C here, the pressure of C, instead of pressure of D, right? You can't really have a pressure of C, it's a liquid, so it won't be exerting pressure, it won't be factored in for equilibrium, and so that was just a complete oversight. I didn't notice that the pressure of D is what that chart should have said. Okay, these problems that I'll address the question when we kind of get to it. Okay, so you should also know that this is definitely chapter 13. We're talking about equilibrium. Okay, and so the pressure, it should have been pressure of D, not C here. And to truly solve for Kc, which is the equilibrium constant in terms of concentration, you actually needed a temperature, which was just an oversight. Okay, so the temperature I'm going to use for this conversion is 298 Kelvin. Okay, and we've gone through lots of these chart problems, so I'm not going to go through it step by step like I typically do. I'm just going to show one example calculation. So I'm going to show minute 0 to minute 1, what we see. Okay, and so I write my pressure, so pressure A, B, and D. I write my initial pressures at time 0, noting that the dash just means 0. And then I'm going to write my change to get to minute 1. Okay, now my change, I'm going to put it in terms of x. Okay, x is just a common number that we're going to use for these. Okay, and so beyond the x portion of this change, right, we have two other portions. We have the sign, right? And so we're going to write negative if it's a reactant. Okay, so A and B are both reactants, so we're going to write negative. And then D is a product, so we're going to write that it's positive, right? And those signs just mean that as time goes on, the reactants are negative, meaning they're disappearing over time, while the products are appearing, hence positive. They'll be more and more as time goes on. And then the last factor are the coefficients, right? And so these are the coefficients from the balanced chemical equations. Really what this is saying is that when 3 molecules of A react with 2 molecules of B, they create 2 molecules of D. Okay, and so these numbers, 3, 2, and 2, come from the coefficients in the balanced chemical equation. And so using these change relationships, we can look at the known values, solve for x, and then apply the change. Okay, and so we have pressure information for compound A at minute 0 and minute 1, right? 3.45 atmospheres and 3.33. Now the change in this 1 minute period is equal to negative 3x. Okay, and the actual value of the change is negative 0.12. This means that just x alone equals 0.04. Okay, now that we know that x equals 0.04, we can just plug it in for the x in this change section to know that the pressure of B should change. It should decrease by 0.08, while D should increase by 0.08. Okay, and so I apply that change, and these are my pressures of D and B at minute 1. Okay, and so that's how I filled in this entire table. Okay, so this is what the whole table would look like. All the red values are ones that you would have had to come up with yourself, right? Black values were given. Okay, and so what you would have done is you would have filled out this chart and gotten these equilibrium values. Okay, now once you had these equilibrium values, right, we want to plug it in to find our equilibrium constant, Kp. Okay, and so Kp will equal the pressure of our products, which, I'm sorry, that should have said pressure of D. Okay, pressure of D squared divided by pressure of A cubed times pressure of B squared. Okay, and so what I did is I plugged in these values, raised them to their respective powers, and found that our K of P is about 0.081. Okay, but this question asked not for our equilibrium constant in terms of pressure, but actually in terms of concentration. Now I would actually write this equation down. It's not one that they typically ask for, but it's one of the few equations that does come up in this course that I believe is not on your equation sheet. Okay, and that's why I recommend you write it down in case you need to use it, because I know in years past it definitely hasn't been on the equation sheet, and I'm pretty sure it's not on yours, but I'm not 100% sure. Okay, so from here I can solve by Kc by plugging in my values, right? So Kp we got above, Kc is what we're solving for, and this is multiplied by R, which is our ideal gas law constant, 0.08206, times our temperature in Kelvin, which I accidentally forgot to give. I would have probably just picked 298, which is 25 degrees Celsius. And then we're going to raise it to the delta N. Now, delta N stands for the change in number of moles of gas. Okay, and so to solve for delta N, you're going to take moles of gaseous product, right, which would be D, and there were 2 moles of that, right? And from that, you're going to subtract moles of gaseous reactant, which there were 5 moles of reactants in the gas phase. There were 3 moles from reactant A and 2 from B. And so 2 minus 5 is -3. So we're going to raise that whole portion to -3. And that should have given us an answer of 1.184 times 10 to the third. Okay. Okay, and here's question 2. Now this is our challenge problem number 2. Now this is the only other challenge problem we're going to go over from last Wednesday, because the other 3, which I'll show you in a minute, we're going to go over those ones on Monday because they're related to chapter 14. Okay, so we're only going over the chapter 13 related questions this evening. Okay, and so you're given a chemical equation at the top, and this general format is the most typical format that you will see Le Chatelier's principle in. Okay, you could also see it in multiple choice pretty easily, but oftentimes it's been a long answer question, and this has been the format. Okay, so portion A, how would we shift if we added 5 moles of A? Okay, so we're always assuming that we're at equilibrium before these changes. Okay, so we're at equilibrium, and now we're adding more reactant. And so we're going to counteract this by shifting to make more product. Okay, so we're going to be shifting rightwards from A. Okay, and as a rule of thumb, whenever you add a reactant or product, you're going to shift in the opposite direction. Okay, so we added a reactant, we're going to shift towards product. Okay, and the little star or caveat to that statement is that you shift to the other side if your reactant or product is a gas or aqueous. Okay, and I think a good example of this is B. Okay, in B, we're removing compound C, which is a product. Now, typically, when you remove product, you would shift that same direction. Okay, so typically, if we were to remove a product, we would typically shift rightward. However, in B, we're removing a liquid, right? Compound C is a liquid. Now, liquids and solids aren't accounted for in equilibrium, which means if we add or remove a liquid or solid, equilibrium will actually not shift in either direction. And so whenever we add or subtract a liquid or solid, there's going to be no effect. Okay, and that's one that they love to include. They love to include that because a lot of times you'll say, oh, you're removing product, we shift right. Well, you have to be careful and look at the actual state. Okay. Now C says you decrease the area in which the system can take place. Basically, I meant like you're decreasing the volume, right? Area was just a general term. Okay, so you're decreasing the region in which these molecules are colliding. Okay, so if we're decreasing the volume, right? Remember that pressure and volume are inversely related. So if we're decreasing the volume, that means we're increasing the pressure. Okay, and when we're dealing with increases and decreases in pressure, remember that we shift to the side that has the favorable number of moles of gas particles. Okay, so here in C, by decreasing the volume, we're really increasing the pressure. Okay, when you have too high of pressure, you're going to counteract that by shifting to the side that has less moles of gas. Okay, so our reactant side has 5 moles of gas. Our product side has 2 moles of gas. And so we're going to shift rightward, right? Because to counteract that increase in pressure, we're going to create less moles of gas by shifting rightwards, which will therefore counteract that, lowering the pressure. Okay, D is the exact same question, right? I just worded it differently. In D, I straight up said, you're increasing the pressure of the system. In C, you had to realize that I was decreasing the volume, which means I was increasing the pressure. Excuse me. Sorry if I keep coughing during this. In E, you lower the temperature. So this is one that would need more information because I don't give you a delta H value, right? I don't tell you if this is endo or exothermic. And that makes a huge difference. And so here, need more information. You have to know that in order to answer the question correctly. And then lastly, F, add a catalyst. Catalysts never affect equilibrium, right? They always have no effect on equilibrium. All they do is help you reach equilibrium faster, okay? But they will never shift or change equilibrium. So if you ever see add or remove catalyst, it should have no effect on equilibrium. Okay, this is number 3 again. This was from last Wednesday, but this will be added to the review video I send out this week. I can answer your question in a minute. I'm sorry. This challenge problem will be added to my video that I post later this week, and we'll review it on Monday as part of the challenge problems when we're covering chapter 14. Okay, and 4 and 5, again, these are pertinent to chapters 14, and we'll review them on Monday. I don't want to take away time from our review tonight. Okay. Sorry, I'm just looking at the chat. Oh, yes. NMI means need more information. Yeah. So are there any questions before we start our review? And maybe indicate this, if you can just sign in now using your net IDs in the chat, this is probably a good time so that I don't miss on any questions. Okay, and so just a general format for this review. So we're going to go through all of chapter 12. Compared to our last review when we went over chapter 12, they're very, very similar. I changed the wording on 1 or 2 slides, but not too much. And then we'll go over chapter 13 as well. I'm happy to take questions as we go along. Just realize if you put your question in the chat, it might take me till the end of the slide to get to it. While if you unmute yourself, I'll probably answer it right away. And then there's also a set aside portion at the end for questions. And we can go until they're all answered. And yeah, I don't think there's any questions in the chat. So let's jump right into chapter 12. Okay, so here's our definition of rate and relative rates. So again, whenever they give you information about a compound and then ask about the rate of that same compound, you're going to use this general formula, right? If you have a compound, let's call it just compound A, and they want to know the rate of disappearance of compound A, you would do the change of concentration divided by the change in time, right? And if you have a negative rate, it's a reactant, positive rate, it's a product. Okay, we also have relative rates. Now you're going to use relative rates anytime they give you information about one compound, but ask about the rate of a second compound, right? And really, you're just factoring in your coefficients here. Okay, I'm not going to dwell too much on this. I would definitely be familiar with this and know this. However, these topics do tend to appear a little bit more frequently on the multiple choice question. Okay, there's just kind of better material to ask on long answer sections. But again, definitely be familiar with it. Definitely know the usage of rate versus relative rates. Okay, now rate law. Now this is the general equation we're going to use for our rate law. Okay, so remember that the units of rate are always going to be molar per time in this course, okay? And so the rate, which is going to be in molar per time, is equal to K, which is our rate constant, and it will vary in both value and units, and then it'll be multiplied by the concentration of each reactant raised to its order, right? And remember that these superscripts in the rate law are experimentally determined, right? They are not equivalent to the coefficients in the balanced equation, okay? They could be, but you can't just look at a balanced equation and know the superscripts. You actually have to go through data and experimentally determine it. Ooh, sorry about that again. So here's one of the edited slides. I just tried to better word how to solve our rate laws in our reaction order based on data, right? So you're going to start by choosing an experiment where only one reactant changes in concentration. You're going to plug that data into this general setup, and you're going to solve for our exponent, right? That exponent is the order of that particular reactant. Okay, once you do that for a single reactant, right, you're going to go back and do it with all the other ones. Okay, and once you have the order of every single reactant, then you can find K by plugging in data from any trial or experiment given. Okay, and so this is your typical way of solving. Now, sometimes you can also have to, there's sometimes where you can't actually solve for the order of a reactant through our typical procedures. And when that happens, you have to use one of two main ways to approach that problem. Okay, the first way you can do this is by making a novel or new trial. Okay, and here's the general setup for it, or the general steps for it. The other method is slightly different. You actually don't need to make a novel trial, but I'm not really going to explain that now. If you want to see the two methods, I would suggest you check out the video I'm going to post tonight, reviewing the challenge problems. I believe number 3 it is. Yeah, number 3 is a question pertinent to this type of question. And I go through both avenues of how to solve it. Okay, so I definitely recommend maybe having these steps up side by side and picking which way you feel most comfortable solving it. But I would definitely make sure that you feel whether it's a novel trial method or the other method, definitely make sure that if you can't solve for the reactant order through the typical means, definitely make sure you're confident in one of those methods. Here's the table I use to kind of keep straight my 0, 1st, and 2nd order reactions. Really what this table shows us is our integrated rate laws and our half-life equations for these three types of reactions. What I'd point out is that although the integrated rate law and half-life equations on your equation sheet, like they're on your equation sheet, they're not labeled. Okay, so I'd say be very familiar with which one is which, what's corresponds to 2nd order versus 1st versus 0 order. If not, I definitely write that down and have that part of your written notes section. Okay, because again, those equations are on the equation sheet. However, they're not labeled for you as to which one is which. Okay. And so we kind of talked about these terms. So what is it? So half-life is basically the amount of time it takes for the reaction to reach halfway completion, right? So how long it takes for 50% of the reaction to occur, or for 50% of a compound to decompose. That's typically one way we see it. The integrated rate law typically allows us to find the remaining concentration of a reactant we have after any given time period, okay? And what this conversely means is that if you're given a concentration, you can actually solve for how much time it took to get to that concentration based on your initial concentration, okay? A naught, or A with this little 0 next to it, that means initial concentration or concentration at time 0. And definitely note that. That's not something that we just see in chemistry. You'll see that a lot in physics as well. Okay, so if you ever see like a 0 next to something, it typically means like a sub or superscript. It typically means original or initial concentration or amount. Just some notes about energy, activation energy and catalysts. So activation energy is the energy barrier that kind of prevents us from converting reactants to products, right? So if you have, if particles have greater than the activation energy, right, they'll easily be converted to products. While if particles don't have enough energy, they actually won't be able to become products, right? They'll kind of revert back to reactants, okay? And this is why we typically see reactions go in just one direction, we don't see both reactions that much. As we learn in the next chapter, all reactions do go both ways some, but the energy barrier, this activation energy, is why some reactions primarily go in just a single direction. Catalysts. Now, catalysts, sometimes you'll see them labeled as enzymes. They speed up reactions, and they do so by decreasing this energy barrier, this activation energy. Okay, it kind of relates to the F portion of collision theory, which we'll talk about in, I believe, the next slide. Okay, they're considered 0 order, meaning if you change their concentration, it doesn't really change the reaction speed. And it's really important to note that they're never used up in the reaction. Okay, so they're the same as in the beginning as they are the end. The last note I would make about catalysts-enzymes is that, again, they are lowering the activation energy, which has to do with the path reactants take while trying to be converted to products. Okay, so catalysts will never affect a state function. Okay, remember, state functions or state variables are ones that don't depend on the path. It just depends on the beginning and the end. Catalysts do not affect those state functions, right? So catalysts do not affect delta H, enthalpy changes, or equilibrium, right? It doesn't affect either of those all it does is lower the energy barrier. Okay. And I told you on the last slide to think of F in collision theory in relation to enzymes or catalysts, right? So collision theory, it says that K, our rate constant, is equal to 3 different factors that we label as P, Z, and F. Now, P stands for orientations. Basically, do our reactant molecules collide at the correct orientation that will allow them to convert to products, right? That's one factor at play. Another factor at play is collision frequency, right? How often do my reactant particles collide together, right? Obviously, we think that if they collide more often, there's probably a better chance they're going to become products, right? And then lastly, we have collision energy. It's actually a fraction. So it's a fraction of the collisions with enough energy. Basically, it's standing for, is it able to, or how many collisions are able to overcome that energy barrier to actually allow us to convert to product. Okay, and our Arrhenius equation is more of a mathematical description of this same relationship, right? We're saying K, that rate constant, is equal to A, which we refer to as our frequency factor, times E, which is just some math number. I think it's like 2.7 something. But it's A times E raised to the negative activation energy over R times T. Okay, definitely note that this R is your 8.31 value. Okay, it's not your ideal gas constant R. And T is your temperature in Kelvin. Now, if you take the natural log of this entire equation, you get the equation that I listed below. And definitely just note that you can turn this into y equals mx plus b form, right? If you graph the natural log of k as your y-axis and 1 over t as your x-axis, your slope is negative activation energy over r, right? So negative activation energy over r is equal to your slope, and ln of a would be your y-intercept. Okay, definitely be familiar with how that can be graphed. But also be very familiar with the second equation, along with this last equation, that CC equation, for catalysis problems. And you'll see a good example tonight in the challenge problems. I believe number 5 is a catalysis problem. Okay, are there any questions before moving on to chapter 13? Okay, if there are no questions, I'm just going to start to move on. Again, there will also be time at the end if things come up. Somebody asked in the chat, is Lna always 1? So no. So first off, in many problems, we assume A is 1, not Lna. When we assume A is 1, ln of A actually equals 0. But also, no, ln of A is probably very rarely equal to 0. But in catalysis problems, that is often an assumption we make. Okay, and it's typically because of a sentence that they put at the end of the problem, where it says, assume all of these have the same frequency factor. Okay, if they make that statement, assume all of these have the same frequency factor, then yes, I would assume the frequency factor A is equal to 1. Therefore, ln of A would be 0, and I continue my calculations. But if they do not say that, you can't assume that. Okay. Okay, and so here's the topics we're generally going to cover in chapter 13. So equilibrium and the equilibrium constant, right? So equilibrium, we learned in this chapter that actually almost every single reaction is bidirectional, right? You're going to see some of the forward direction, but also some of the reverse direction. Now, sometimes we see one of the reactions, either the forward or reverse, is predominant. And the reason for this is the activation energy, or that energy barrier we talked about just a couple slides ago, right? So if the reverse reaction has a really high energy barrier, while the forward reaction has a very low energy barrier, then we will almost exclusively only see that forward reaction. Okay, and so that's why sometimes we only see it one ways, but now we're actually starting to admit, no, okay, for the most part, we've said reactions go just in the forward direction. Now, let's take a step back and realize how they go in both directions. Okay, and so K is our equilibrium constant, and what it really is, it's a ratio of our rate constant of the forward direction divided by the rate constant of the reverse direction, right? So this portion's related to chapter 12, those rate laws, which in general is a ratio of products divided by reactants. And this is going to be equal to the concentration of our products raised to their respective coefficients divided by the concentration of our reactants raised to their specific coefficients. Okay, and so what I'd remind you here is that your superscripts in this formula comes from your balanced chemical reaction. Okay, this was not the case for rate laws, right? This was not the case in rate laws where you have to experimentally determine your superscripts, but for equilibrium constant, it is your coefficients that become your superscripts. Okay, and we can solve for our equilibrium constant in terms of molarity, so things in the aqueous state dissolved in water, or things that are gases with pressures that are measured in atmospheres. Any reactant or product that is a solid or liquid will not be accounted for in this equilibrium expression. Okay, just a quick note, when you're solving for K or equilibrium constant, it has no units. Okay, so if they ever ask for it, you never need to put units for it. And then lastly, again, if you didn't write down this equation, I do recommend it. Just because, again, I don't believe it's on your equation sheet. And it's just relating our equilibrium constant in terms of pressure and concentration. Again, R is our ideal gas law constant, T our temperature, and delta N is the change in number of moles of gas. And remember, change would be final minus initial, which in terms of a chemical reaction is moles gas of product minus reactant.
I have a quick question.
Yep.
So if your product is a solid, then when you're like figuring out what the equilibrium constant is, would you just put 1 over the reactants?
Yep. Absolutely.
Okay. Thank you.
Yep. No problem. And I'll say just kind of a note for that, you could potentially see that. For chapter 13, that's pretty rare. In this chapter, it's more likely that it would be a reactant that's in the solid state. However, the scenario you pointed out is possible to see in this chapter, and you'll see it more often in a couple chapters from now. I believe that's what chapter 16 is all about, kind of forming solids and also the dissociation of solids. So moving on to the reaction quotient, which we represent by the letter Q. And so really this is tracking our progress towards equilibrium, right? So this can show us, have we shot past equilibrium? Have we not reached equilibrium yet? Or it's even potential that you're at equilibrium and just don't know it yet. And so we actually calculate it in the same exact way we calculate K, or equilibrium constant, right? The reason why we use Q is we use it when we are not sure if we're at equilibrium. Okay, so unless they say you are at equilibrium, here are your concentrations, then you should really, to be proper, write Q. Because again, you're not actually sure if you're at equilibrium or not. okay? And so the typical problem is they'll give you data to solve for Q, and then they'll give you the equilibrium constant in the problem. And they basically want you to compare your calculated Q versus your given K, and then state the direction of the reaction. Okay, and again, remember that Q and K generally are products divided by reactants. Okay, and so if Q is less than K, right, that basically means you have too many reactants and not enough products to be at equilibrium. Okay, and so you're going to reach equilibrium by making more products from your reactants, which you do by favoring the forward direction, right? When Q is equal to K, right, that just means you're at equilibrium. And so no specific direction is really favored in that case. But if Q is greater than K, again, that means you have too many products and not enough reactants, right? Because the number's too big to be at equilibrium. And so what you want to do is you want to take some products and make them into reactants to reach equilibrium. And so whenever your Q is greater than your K, the reverse direction, your right to left reaction, is going to be favored. Okay. Manipulations of K. So sometimes you might have to change a chemical equation. These are the three most common manipulations you'll have to make to an equation and how you adjust your equilibrium constant accordingly. Okay, so if you reverse a reaction, and sorry, it's just a little side note, definitely remember these because this will come up again and again this semester. And I think it's tricky because it's actually different from thermochem, which again will come up this semester and we learned last semester. Right, so in thermochem, when we reversed a reaction, we just changed the sign on delta H, right? We just made it from negative to positive or positive to negative. But when we're dealing with equilibrium constants, if we reverse a reaction, so we flip it, we actually take the inverse of the K, right? So if our equilibrium constant for A to B is 4.38, the equilibrium constant for B to A would be 1 divided by 4.38, which would actually be 0.228. Okay? If you ever have to multiply an equation by a coefficient, you're going to raise that equilibrium constant to that coefficient. I wrote exponent. I meant to change that. Okay, so if you wanted the equilibrium constant for 2A goes to 2B, you're going to take your original equilibrium constant, 4.38, and square it, right? Because that's the coefficient you multiplied this whole equation by, which gets us 19.18. And then if you ever have to add equations together, you just multiply your equilibrium constants together. Okay, I will attest that this was personally on my long answer portion of the Chapter 13 exam. Okay, so this has appeared on the past, so definitely don't overlook this. If you haven't done it yet, I believe last Monday's SI session, I believe I gave a good example problem of this and how you could see it on the exam. Okay, so the challenge problem was given last Monday, and we went over it last Wednesday, I believe, where it's a manipulation of K problem. Okay, types of problems. So just kind of some example or types of problems I wanted to go over. We have three kind of classic types of questions in this chapter that are mathematical based. There's actually more. These are just ones I specifically wanted to talk about. Okay, so there's the classic table problem, which is what we went over in the first challenge problem today. It was number 1. And here, this type of problem, you're given a table that's partially filled out, and you're basically asked to look at the change in pressure concentration, to solve for X, and then based on X, find the change for each reactant, right? Again, think of number 1, how, maybe the pressure of A decreased Then we solve for x based on what the change is in terms of x. And then we applied that change, that x value, to our other reactants and products to find at minute 1 what those concentrations or pressures are. Okay, in this type of problem, you typically fill out the table till equilibrium, and then you plug in the values into our equilibrium constant expression to solve for that. Okay, so these classic table problems, typically your end goal is to solve for your equilibrium constant. Now in this chapter, we introduce ice tables. Okay, now in ice tables, these are different because they typically will give you a starting concentration of reactant, but they'll almost always give you the equilibrium constant. Okay, so in this chapter, in chapter 13 ice tables, they'll give you the initial concentration of reactant and your equilibrium constant. And what you're actually going to do is make an ice table in terms with your change in terms of x, solve for your equilibrium concentrations in terms of x, and then set that equal to your known k value to solve for x. Okay, so realize in these table problems like number 1 this evening, you're actually solving for k. In these ice table problems, you're actually going to be solving for like that x value. That's kind of the end goal for the problem. And then solids and liquids, this is just kind of a special type of ice table problem where typically you'll be solving for the pressure of a gas, which is often a product, and then you can use the ideal gas law to convert from pressure of gas to moles of that gas, and then you can use stoichiometry of your balanced chemical equation to then find out information about a solid or liquid, right? Because we can't use equilibrium to directly tell information about a solid or liquid, okay? And again, my last note before changing the slide is these are just types of problems I wanted to highlight. I really didn't mean for it to seem like these are the only types of problems in this chapter. You definitely should be able to calculate Q and relate that to K. And then Le Chatelier's principal problems are also very common. Okay, but those two, along with these 3 topics, are pretty substantial sections of this chapter. Okay, now this is a problem we actually did previously, so I'm not going to dwell on it too long, but really this is an example of the ice table problems I was talking about and what to do when they ask about solids or liquids. Right, so they give you a bunch of information about this. They give you an initial pressure of oxygen, a temperature, of volume, and they tell you the equilibrium constant, right? So what I want to draw your attention to is they give you an initial pressure of oxygen, which is a reactant, and they give you the equilibrium constant. Okay, when they give you those 2 pieces of information, you should be forming an ice table like this, right? And you ignore anything that's a solid, right? So I'm going to ignore the solids, and I have my initial concentration of oxygen. I'm going to assume no concentration of water originally. And then I'm going to write the change in terms of x, right? So it's going to be minus x for oxygen because it's a reactant, so minus, but also its coefficient is 1, which is why it's minus 1x. Water, however, has a coefficient of 2, so it's going to be plus 2x for water. From there, you'd write your equilibrium concentrations or equilibrium pressures in terms of x, right? So 2.1 minus x is our pressure at equilibrium for oxygen, and 2x is our equilibrium pressure of water vapor at equilibrium. And we're going to plug this in to our equilibrium expression, our equilibrium constant expression, and they gave us that value was equal to 32.6. Okay, so from here, we solved for x, which ended up coming to 1.73, right? When you use the quadratic formula to solve for x, you'll typically be given 2 values, only one of which is actually possible when you plug it back in, right? This negative value would have given you a negative pressure of water, which is impossible. So we know that it could only be this 1.73 value that works. And from here, we can substitute this value in for x and find that at equilibrium, Our pressure of oxygen is 0.37 atmospheres, and our pressure of water is 3.46 atmospheres. Okay. Now that we have the pressure of water, we can actually use our ideal gas law to solve for moles of water, and then they ask for grams of beryllium synthesized during this. We just do the moles of water. We use our balanced chemical equation to convert to moles of beryllium, and then the molar mass of beryllium to solve for grams. Somebody asked in the chat, is the negative value that results always the one that's impossible? I wouldn't say always. So you could write positive X for a reactant and negative X for a product. In their case, your correct answer would be negatives because the double negatives would actually cancel in that case. So in that case, your negative sign X would be correct. I also have seen problems where you get two positive values for X. Okay? And if you get two positive values for X, the one that is incorrect, right, you should still plug them both in, but typically one of the values is so big that when you plug it in for the minus X portion, then your reactant becomes negative in pressure or concentration. Okay, next question. So Kayla asked about 2.1 minus X on the homework. If you want my honest opinion, I would say don't use that assumption. Okay, so to repeat the whole question, said on the homework, we assumed that 2.1 minus X was just 2.1. Will this be the case on the test, or do we use the quadratic? So you're making an assumption by ignoring X there, and that will not always be correct. Okay, that's one of the things I'm going to cover in the video that I post later this week. But it is possible that if you ignore X, you will get the wrong answer. Okay, and so I would encourage you, until you fully know how to make that assumption, to use the quadratic formula. Because the quadratic formula, assuming you plug it in right, will always, always, always give you the correct answer. Okay, it's not always the easiest to do, but quadratic formula will always give you the correct answer. While again, if you drop X, so you assume 2.1 minus X is just 2.1, it is very possible that that would give you an incorrect answer. Yep. And if you do, before the exam, want to watch the video I post to see how to do that assumption, you're welcome to. But it's one of those things that it does often work, but you actually have to check it because there are instances where it won't. So I don't want you to kind of prematurely do that. Okay, now the last topic to cover in this chapter is Le Chatelier's principle, which basically states that if you're in equilibrium and then a manipulation is done on the system, that the system will respond by resisting the manipulation. Okay, and I kind of think of this as, again, I was a biology kid in college. I think of this as basically chemical homeostasis, right? You're trying to stay at equilibrium. So whenever a change is made, you're going to do anything that you can, or you're going to really shift in one direction or the other in order to kind of come back towards equilibrium. And so listed here are the manipulations that you should understand. I would also add catalyst to this. You should definitely know what happens when a catalyst is added to this, but you should know what happens when you add or remove a reactant or product. You should know what happens if your volume or pressure changes, right? And so just realize that these are inversely proportional. Okay, so typically a volume change will occur, which will cause a pressure change, and based on the pressure change, you shift to one side or another. And again, you should know temperature. Okay, so know what happens if it's an endothermic reaction, an exothermic reaction, so on and so forth. Okay, there will be another example of this, Le Chatelier's principle, in the challenge problems tonight. Okay, I know they're kind of redundant. There's really only so much you can ask in terms of it, but I'm hoping plenty of practice is helpful, and hopefully now you're not just starting to say which side because you think you know the rules, but you're actually understanding why each manipulation causes their respective shift in equilibrium. Okay, without further ado, again, that's all I really have, but I have set aside this time to take any questions. For now, I will keep this recording and answer questions, but after a bit, I might just stop the recording. But even when I'm do that, I'm happy to stick around and answer. I honestly can't answer that question. So Lizzie asked, will we be deducted points if we don't use the quadratic formula? I use my graphing calculator. So this is a portion of the class where you guys are kind of lucky it's online. Typical chemistry exams, you are not allowed a graphing calculator. You have to use the really old-fashioned ones where you're going to put your parentheses wrong and it's going to mess up the entire problem. It was definitely a tough one to do. So we were only allowed to use very, very simple calculators and like no written notes, like anything like that. So really any questions about your notes or your calculators, definitely direct it towards your professors. Especially, I'm pretty sure you need to send your work. So I don't know. I think if you maybe put it in the format, 0 equals ax squared plus bx plus c, you put it in that general form and then use your calculator to solve, I think that would be fine, but. Okay, yeah, there's no practice exam. It's another, yeah, I wouldn't rely on future practice exams from the professors. That is something, again, that is, when it moved to the online format, they typically would give like 1 or 2 for the first couple, but that's not something they typically do from semester to semester. And so again, when it's provided, it's an awesome resource, but I definitely wouldn't rely on that.
I have a question about the Le Chatelier's principle.
Yes.
Could you please go over how the equation would shift if the temperature would change, like endothermic versus exothermic, how that would differ?
Yeah. So endothermic means into, like thermal energy into the system. And so heat in an endothermic reaction, which is a positive delta H, heat is actually a reactant. And so that's actually how I'll address it later when I go over these challenge problems. Sorry, I just kind of had a blank. So endothermic reactions, heat is a reactant. Exothermic reactions means heat leaves the reaction, meaning heat is actually a product. And so what I physically do, and again, exothermic reactions have a negative delta H, what I do is I physically write that into the equation. Okay, and so if they say, whatever, you have an exothermic reaction, and let's just say it's just A goes to B. So if we know delta H is negative, I'd write A goes to B plus heat. Okay, again, I write it directly into my equation. Now, once you write it into the equation, temperature changes are actually like adding or subtracting reactant or product. Okay, so let's again stick with our example of A goes to B plus heat, right? It's an exothermic reaction. If you increase the temperature, it's the same thing as adding heat, right? And so if it's exothermic reaction, heat is a product, and so it's like adding product, causing you to shift leftwards towards the reactants, okay? If temperature is lowered, it's like removing heat, okay? So for our equation, A goes to B plus heat, you're removing product, causing you to shift rightward towards the products. And same thing goes, the same logic goes behind endothermic reactions. It's just in that case, you would write heat on the reactant side. Does that make sense?
Okay. So for like the example you said, so exothermic, when you increase the temperature, it's like adding product, is what you're saying?
Yep.
Okay. All right. Thank you.
Yep. Of course. Yep. So increasing temperature is like adding. If you decrease the temperature, it's like you're taking away. It's like you're removing. So they cannot make you in. So Ariana asked, would they tell you if it's endo or exothermic, or is there a way to infer? So they'd either give you a delta H value, right? So positive is endothermic, negative is exothermic. They could tell you it's endothermic or exothermic. And those are the only real two ways that they would expect you to know. The other option is that they wouldn't tell you, and that's where the option of need more information would come in, right? Because you're saying, I know changing the temperature has an effect, but I need to know, is it endo or exothermic? Because based on that, my answer will vary. And so if on the exam, they don't tell you if it's endo or exothermic, but they want you to know how the temperature change would affect equilibrium, you would answer need more information. Yeah. Yep, that's actually typically the way that need more information comes up on these exams. Okay, and those wording, how I worded that, these Le Chattier principle questions, I have not changed from how I saw it on my exam. Okay, so does it shift right, left, no effect, or need more information? That's just kind of standard of how they've used it in the past and probably will continue.
Would there ever be a situation in which like there are multiple manipulations?
No. They would do them as like how I do them. So, you know, maybe it's a long answer question. There's 6 of them. They're each worth 2 points or something like that. They wouldn't have you kind of compare how one may have a greater effect than another. It would just be one at a time.
Okay, thank you.
Yep. Any other questions? Okay. There aren't. I'm just going to stop the recording here. But if there are questions, those people can stay.